Hello, and welcome to our lesson 2, unit 4, graphing quadratics. And here we're going to be talking about transformations of functions. So there is, in fact, I would say, is it an easier? Yeah, there is, in fact, like another way to think about, um, you know, how to graph a quadratic function and really talk about it in terms of what transformations are occurring to this from our original graph. So transformations are basically where you stretch, compress the graph, you reflect the graph, and you move it left or right. And you've hopefully done, those of you who've you've probably seen transformations before in like grade 7 or 8. If you, of course, you did your schooling in Ontario. I think I'm pretty sure you covered transformations um, before this. At least, when you move things, like when you move a shape 3 units to the right or 4 units down and things like that. So that's basically what a transformation is, or what kind of transformation. So we're going to be talking about, and the really the transformation formula is the same as our vertex form. That's why we're talking about transformations now. And this is kind of why, like I said, we're talking about it now. And each of these letters here, the A value, the H, and the K, have different effects on our graph. So we're not going to talk about the H comma K vertex for now. We're just going to talk about what does the H value mean for our graph in terms of where the graph is moving. And of course, the original function, it has to move from somewhere, and the original graph is y equals x squared, like this graph right here. We're talking about moving this graph. So for example, if I had y equals x squared plus 5, we know that this graph is moved 5 units up. So that's what we're going to be drawing, and I can automatically just move this graph 5 units up and very quickly draw this graph right here that looks exactly like that. And this is the transformed graph, right? So I want to be able to do that quickly without having to think about graphing like the last time. And that's what transformations are used for. Of course, there's a lot of other practical uses for transformations. You'll see most of them you'll see a lot of them in grade 11. So it's good practice for next year, hopefully, in grade 11 math. So where was I? Yes, so that's, again, just taking so this is the K value, right? And K value means that I'm moving it up 5 units. So we're going to see what each of these letters mean in terms of what happens to the graph. So the first thing that happens is a reflection on the function y equals x squared. So of course, the form looks like y equals negative x squared. And because, the idea here is that if your a value, or if your graph is positive, if the a value is positive, your graph looks exactly like the original y equals x squared graph. So this is a positive a value. If you have a negative a value of y equals negative x squared, like this graph, as we'll remember from our first video, looks like this. So what I have done is I have vertically reflected it across the x-axis. It's important to use all the terms here. It's very important to say vertical reflection across the x-axis, because that's what we're doing. We're like closing this over like that way. So it looks bad in 2D, but hopefully we see this is the x-axis, and we've reflected it across that. So we kind of flipped it across the x-axis vertically, right? So we vertically reflected it across the x-axis. And that's kind of important there. In terms of the transformation, what happens really is the point x comma y. So if this point was 1, comma 1 on the blue graph, on the red graph it's 1, negative 1. 2, 4 becomes 2, negative 4. So that's what the transform function looks like. You just, the y value has a negative sign in front of it, compared to our original graph. That's that. So that's the reflection part. And hopefully you're just recognizing where there's a negative a value, and you can just graph the reflection. So this is usually where people are kind of confused, but because we're not doing horizontal compressions or stretches, it's nothing to be too worried about. So the idea here is depending on our a value. So this actually, it's good to take a look at our previous graph here. Okay, so let's see what this says. If a value, again, completely ignoring the negative sign. So the negative is already taken care of. So it doesn't matter if the a value is now positive or negative. We're just looking at the number. So if the number on the a value is greater than 1, the graph is vertically expanded or vertically stretched by a factor of a. And for a good example of that, we will look at the graph that we drew here, and hopefully we'll see that this graph is like kind of skinny, or it's like stretched out. So basically I have stretched this graph like so, right? And so it's getting like skinny. So you can't see my hands when I'm doing this. I can't change it. Okay, so hopefully we're seeing that I'm vertically stretching it. My arrows are pointing vertically, like up and down, and I'm stretching this graph, so it's becoming like more skinny. And my a value here, again, we're ignoring the negative. That means it opens down. We've already reflected it across the x-axis, which means opens down. And our a value here was 3, which is bigger than 1, right? So it's a stretch. It's a vertical stretch by a factor of 3. We'll go back, and if a value is a fraction, I shouldn't say a fraction, if it's a fraction that's lesser than 1, if it's a proper fraction, if the value of a is between 0 and 1, which means things like, half, 1/4, 1/3, 5/6, any of those a values, the graph is vertically compressed by the factor a. So I will show you again what that means from the previous graph. You'll see here that this graph is a bit, again, pardon my language, a bit fatter than the previous graphs. And that is because, like, from a y equals x squared graph, from a standard graph, we have vertically compressed. We have squeezed this graph so that it becomes a bit more wide, basically. So that's basically what a vertical compression would look like. And because the a value here is a half, which is again between 0 and 1, right? So that is a vertical compression of half. This is a vertical stretch of 3, right? And that's basically what the a values are telling you. So yeah, that's basically that. The point x comma y, we already know, becomes a y on the transformed function, because we have to multiply the y value by whatever this a value is. That's why when we went, instead of like 1, 4, 9 up, we went like 3, 12, and 27 up, kind of. And again, this is the last bit here. We're going to talk about translations of the function y equals x squared. And the first translation is the horizontal translation. This really has to do with our h value. And again, you'll see here that it's very important to correctly identify what my h value is. Again, from before, I will point out that if I have something that looks like x minus 2 squared, my h value is actually positive 2, right? Very important. So when I have like x minus 2 squared, the h value is actually bigger than 0, so the graph moves right 2 units. So graph of y equals x minus 2, if this is the original graph, y equals x squared, I've moved right 2 units, and this is my new function. Right, so it's very important to see that if I have an x minus 2, I'm actually moving to the right, because my h value is positive 2. Again, very important to note this negative. This is, I'll tell you, this is what confuses most people in grade 10. This is where they slip up. They forget to change the sign of the negative. So the opposite example, if we had, for example, an x plus 7 squared, we'll note that when we label our vertex, we have to take the opposite of this. We have to flip the sign, right? So h actually equals negative 7. So our h value is lesser than 0, so it's translated to the left h unit. So our graph will be somewhere over here. Y equals x plus 7 squared. So when I have an x plus 7, I'm actually moving the graph to the left. So it's kind of opposite than what you normally think, but not really, because if you look at the h value, it's really if the h value is positive, you move it to the right. If the h value is negative, you move it to the left. It's just if the h value is positive, inside the function, it's going to look like x minus 2. If the h value is negative, inside the function, it's actually going to look like x plus 7, which is the kind of confusing part here. But again, the technical term here is horizontally translated to the right or horizontally translated to the left. Again, very important to remember this terminology and kind of make sure that you're using it whenever you answer questions. And the easiest one is a vertical translation. Again, note that this is a translation. Translation is like a shift. You're just moving things up, down, left, right without changing the size of it. Yeah, that's the technical. Translation is a term you should be using. So again, the vertical translation, this is super easy. You just have, y equals x squared plus 3, which is just on a graph of y equals x squared. You're just moving it up 3 units. So it's vertically translated up 3 units. There's no kind of changing signs. It's just, you just look at it. If it's plus 3, you move this up 3 units like this. This is y equals x squared plus 3. And of course, we have the opposite way. Y equals x squared minus 8 is a vertical translation down 8 units. So y equals x squared minus 8. Note that just because it's negative, it still opens up, right? Our a value is still positive 1. This is, again, people might get confused. Shifting down means I just take this graph and I just move it down 8 units. That's it. I'm not changing, I'm not flipping it, I'm not stretching or compressing it, I'm just pulling it down 8 units, right? So it looks the exact same as just moves down 8 units, right? So be careful there. Don't do any flipping. It's just moving down. The a value is still positive 1, so my graph is still going to have step values of 1, 3, 5, or like pattern values of 1, 4, 9. And when you're describing transformations, you have to do it in this order that is given here. First, you do reflections, then you do stretches, then you do translations, because you have to kind of follow BEDMAS. If you kind of translate it before you stretch it, you might go wrong. So it's important to it's important to reflect and stretch before you translate. Again, just follow the pattern that you see here. Reflections first, if any, then you do stretches, then you do translations. Very straightforward. So again, hopefully we're okay with the things that are going on here. And of course, we are going to take a look at graphing these functions. So again, most of the graphing is going to be the same as we did last time, but we're going to simplify things a little bit, but we are going to describe the transformations first. So first, okay, again, it's if you think about it systematically, you can't go wrong. Okay, first let's look for reflection. A value is positive. There are no reflections. That's it. So no reflections. Then we look for our a value is 2. So we're going to say vertically stretched or expanded by a factor of 2. Next, we're going to look at our translation. It doesn't matter which order. I'm just going to do the horizontal one first. Again, x minus 3. So our h value is actually equal to positive 3. So I'm moving it right. So it is horizontally translated right by 3 units, or horizontally translated 3 units to the right, same thing. And our last one, of course, is our vertical translation. So we're going to write vertically translated down, because it's a negative 2, right? So our k value is negative 2, so we're moving it down by 2 units. So I'm going to continue with this question. Our vertex we hopefully get from before, h value is 3, comma, negative 2. Direction of opening is up because our a value is positive. The equation of axis of symmetry is x equals 3. And I am going to graph this kind of the same way I've graphed things before. I first take my vertex to be 3, negative 2. That's right here. And now I'm going to use step values of, instead of 1, 3, 5, my step values are now going to be 2, 6, 10, right? Because I did 1, 3, 5 multiplied by my a value, which was 2, right? So I get 2, 6, 10. So I go 1 and then 2 up, 1 left, 1, 2, 3, 4, 5, 6 up, and then 1 more, and then I go 10 up, but I'm not going to reach there, so that's fine. I'm just going to make this symmetrical around my vertex and graph my parabola. Of course, I do have to label stuff. What is this vertex? 3, comma, negative 2. X equals 3 is axis of symmetry. And of course, I will finally label this parabola. Y equals 2 there. Ta-da! That is my parabola. Again, hopefully we'll see that it's not too difficult. And just the only new things that we've learned here are really writing out these transformations. Because it's given in vertex form, it's easier. I think it's easier to graph just the way we've been graphing before. But of course, for this question, we will show you how to graph. I'll show you how to graph using the transformations on this function. I don't know if is that the way it's done. Let me just check the answer sheet and see how Mr. Tremoli wants us to graph these things. In the meantime, we'll just do this transformations while it's loading up on my other screen. First, okay, any reflections? Yes, I do have a reflection. So the first thing I'm going to say is it's vertically reflected. I hate it when my pen is slow. Over the x axis. Ta-da, that's my first line right there, nice and easy. Again, you don't have to say by a factor of anything. It's just, that's just the negative sign we're taking into account, and we're saying vertically reflected over the x-axis. The a value here is 1, so that is normal. We don't have to say anything. It's not stretched or compressed. So we'll get to our translations. Again, we'll make note that our h value is actually equal to negative 1, right? We have to flip the value that's inside the bracket. So we're going to say horizontally Hold up 1 second. Hello. Sorry about that. Well, I just oh, 1 minute. Domain. Okay, sorry. I just wrote this thing so that you wouldn't have to watch me slowly, painfully write all that on the screen. Again, horizontally translated left by 1 unit because h is -1, and vertically translated up by 5 units because our k value is +5. Again, one thing you can do is identify what your h value and k value and all these things are, so that kind of gives you a better idea of what to write. Right? A equals 1, but there's a -1. Again, be careful. The negative really just, it's its own thing, right? If you see a negative sign, technically it is part of the a value. Like the a value here is -1, but the negative has its own separate transformation than the actual number that's the a value, the magnitude of the a value. The magnitude just means you're not caring about the sign. It's just what number is there. Is it like 3 or is it half? Or is it like 5 or is it 1/3? That kind of thing. To tell you whether it's vertically stretched or vertically compressed. That's important. Here, of course, we will take a look at our vertex. Our vertex here is -1, 5. Direction of opening is down because our a value is negative. Equation of axis symmetry is x equals to -1. And we will, of course, graph this properly. -1, 5 is over here. My step values are just 1, 3, 5 because, and of course, I mean, I have to multiply that by -1 because my a value. So I'm actually going down -1, -3, and -5. So I go 1, down 1, again across 1, down 3, 1, 2, 3, cross 1, 1, 2, 3, 4, 5. Now that I have these points, I'm just going to make it symmetrical looking on the other side. Like so. Join my points. Et voila, I have a parabola. I'm just going to label some stuff. -1, 5 is vertex. That was a very poor choice in placement because that just crosses through my line. But oh well. You win some, you lose some, I guess. X equals -1 is my axis of symmetry, and I'm just going to label this y equals -x plus 1 squared plus 5. There. That is my parabola graph. I do believe on the answer key there is a bit of extra bit added talking about domain and range, so we'll quickly cover that as well. The domain is basically, okay, if I look at my parabola, what are all the x values that are covered on my graph? So I'll see here that I cover like pretty much like all the x values because my graph goes on forever. So if you keep extending this graph, it'll keep going until all the x values here are covered. And if you keep extending the graph this way, it'll keep going until all the x values are covered on this way. So for whatever x value I take, I'll be able to draw a line up or down, whichever way, and I'll be able to touch the graph. That's the idea here. Whichever x value in either direction, because at some point this graph, like somewhere far into the future across this page, will touch this line, right, or this line, or wherever I take. So my domain really is written as x element x e. This e with like a curvy thing is the mathematical symbol for element. So x element of real numbers. So real numbers is just an R with a line that's like next to the thing. My real numbers is not exactly like very nice. Technically, you got to leave a bit of space there. That's like the proper way, I think, to write real numbers. The symbol for real numbers. The real numbers, okay, for those of you who are a bit confused, real numbers is like all the numbers, including like rational numbers and like numbers like pi and square root of 2, and all those fall under the gap of real numbers, because each of those numbers are on the x-axis, and each of those numbers will have a corresponding, will touch the graph at some point. Our range is basically the same thing, except we're talking about what our y values are. So here we're always gonna start writing YER, but there are gonna be some exceptions to this rule, because if you take a look, we know that this has a minimum value of y equals -2. And why do we say that? Because, okay, if you draw a y value like here, we know that it touches the graph, right, at certain number of points. But we can also appreciate, hopefully, that this y equals 5 the graph will never touch this y equals -5 line. Why? Because this y equals -2 is the minimum value. So our range is limited. Our y values are limited so that y has to be greater than or equal to -2, right? Because -2 is the minimum. So y has to be greater than -2. Y cannot be lesser than -2. You will never, in this graph, you will never ever see, if you were to like write a table of values, you will never ever see a y value of like -3 or -5 or -2.1 or -10, because all those values are lesser than 2, which is not allowed, because 2 is the absolute minimum value. And the same way here for a parabola, our domain is always x element of real numbers, and our range is y element of real numbers, with the caveat, or you just put a bar and say with the exception that, or with the restriction that y has to be lesser than or equal to 5 in this case, because now I have a maximum value, right? And this maximum value of 5. So I can have a y value of anything that's lesser than 5, because this goes on down forever, right? It keeps going down and down. So I can have a y value of like -10,000, because at some point, this y equals -10,000 will touch the graph, but I can never have a y value of +7 or +6, because 5 is my maximum. So y has to be lesser than or equal to 5 is what I put in my range. So that was a brief. I don't know if you really need to know that. To be honest, it's good to know. Again, in terms of what is going to come on an assessment, you probably have to take a look or ask Mr. Tremoli. I'd actually go to Mr. Bosse's video and look to see if he's done or if he's talked about domain and range. I just talked about it because I see it on the answer key. I think hopefully that is the right answer key. I'm not looking at another version or something. Yeah, I'm pretty sure it's there on the answer key. So it's I just mentioned it, so it's good for you to know these things. But of course, I'm not 100% sure whether it's actually going to be tested. So hopefully, again, transformations are okay. As we see, it's not really too complicated as long as we know our h value, a value, k value, and you just have to remember these things that we've talked about. You just have to remember this table, essentially, and as long as you remember that table, you're pretty good. You're pretty solid, right? So I will see everybody, or I will talk to everybody very soon. We're going to be doing lesson 3, of course, which is actually not that big a lesson. It's very easy. We're going to be talking about some algebra. There's no there's not much graphing going on here, so that's I guess good. It depends if you like graphing or not. So I will talk to you soon. Until then, peace out.